let us revisit the case study set of all strings over 0, 1 ending with 0, 1. The regular expression is precisely this 0 plus 1 star 0, 1. The finite automaton is this. Note that delta of q0, 0 is q0, q1. So it is moving to more than one state, and that brings non-determinism. So this is a non-deterministic finite automaton. This one is a subset of q0, q1, q2. In general, it is a subset of q, or it's an element in power set of q. What is a power set? Set of all subsets of q. Now, the interesting question is, can we come up with an equivalent DFA? Is there a procedure using which one can obtain an equivalent DFA? So, we have to come up with a deterministic finite automaton whose language is same as precisely this. And the automaton must be designed in such a way that for any state on an input symbol, it should go to exactly one state. It should not go to more than one state. Fine? And that's precisely the focus. We shall next see how to design such a automaton. So we start with Q0, the start state of NFA and DFA are one and the same. Then we look at delta of Q0, 0, which is Q0, Q1. So we generate a subset. What we do, we create a state which is labeled as Q0, Q1. To maintain consistency, what I do, even this I list it as set containing Q0. So on reading 0, we go to this state. Then Q0, 1 is Q0. So we stay in this state. So next, now you treat this itself as a state just like Q0, Q1, Q2 and apply the possible inputs. So now this one is defined as Q0, 0 union delta of Q1, 0. Delta of Q0, 0 is Q0, Q1. And Q1, 0 is undefined. So you can even assume this to be empty set, and if you take union of this, you get this. So what this says is, if you read a 0, you stay in the same state. So delta of Q0, Q1, 1 is delta of Q0, 1 union delta of Q1, 1. So on reading 1, this says you stay in Q0 union. On reading this, this says Q2. So we get a new state labeled Q0, Q2. What this says is, when you read a 1, you go to a state which is labeled Q0, Q2. Now similar to what we did, you treat this as a state and apply the transition. Now this is delta of Q0, 0 q naught comma 0 is q naught q1 union q2 comma 0, which is undefined. So what we get is q naught q1. Correct? So this says on reading a 0, we go to this state. Now delta of q naught q2 comma 1 is q naught comma 1 and q2 comma 1. q2 comma 1 is undefined. So q naught comma 1 is q naught, which means on reading 1 we go to this. That's all. So the idea is this: we start from q naught. Whenever we generate a new subset, we start applying all possible input symbols from sigma. So we applied 0 and then we applied 1, and on applying 1 we generated a new subset. Again from this apply 0 and 1, but it turns out that on application of 0 the output was this, on application of 1 the output was this. So we have not generated any new subset. We can stop our algorithm. Because we generate subsets iteration after iteration, this procedure is called, or this method is called subset construction method. By generating subsets of this set q0, q1, q2, we find another automaton which is equivalent to this. Most importantly, the automaton is deterministic in nature. Look at this. On reading 1, we go to exactly one state. On reading 0, we go to exactly one state. On reading a 0, it's 1. On reading 1, exactly 1. And this is precisely what we initially defined for this question, and that's precisely what we have also obtained now via this subset construction method. Now these are all some states. You can relabel them as say A and B and C, and then rest of them are same. The whatever we discovered above, the same transitions are applicable here as well. Now this clearly says it ends with 0, 1, and you can read any number of 1s followed by 0. If you want to read some more zeros, you read here, then end. And at this point in time you want to go back, so if you read a 0, and you should end along with 1, which is why we come here. But if you read a 1, you have to again read 0, 1, which is why we come back here, ensuring that we read 0, 1 again. And which is a final state. This contains Q2, which means this one is our final state. This one is our final state. So through this subset construction method, given a non-deterministic finite automaton, one can construct an equivalent deterministic finite automaton. Now this can grow, meaning if there are 3 states here, it may so happen that we may generate all subsets, meaning we may get 8 states, and leave empty state, we may get 7 of them. And in general, if there are n states, it may so happen that we may generate all 2 power n minus 1 subsets as part of our construction. So the number of states increases by bringing determinism into the context. A non-deterministic finite automaton having n states if you try constructing an equivalent deterministic finite automaton following subset construction method, we may end up getting a deterministic finite automaton having maximum 2 power n minus 1 states. Okay, but we are interested in the determinism, so we are not concerned about the number of states in DFA. As long as it is deterministic in nature, we are fine with that. Okay, but one has to remember that this conversion is kind of exponential in nature, meaning if this has n states, you may end up getting a deterministic finite automaton having maximum 2 power n minus 1 states. Fine.